Okay. What's up, guys? Today I visit C Action. I'm working on New York. And diving into we are working on a tool that I've been working on. That is just a C-based, C command line based resizing tool. Just something quick that you can use in your command line to just, hey, give me this image, some example use. Let's look at some example usage. You know, some example usage, you know, we're calling it imagey. Hey, I want this picture of me naked to be this size, and we'll make it that size. Now, there are 1 million different things we're going to have to consider. As you can see, my mess of code here. Music may be a little bit loud. So, where are we at so far? What are we doing? We can give the code an image. And what that code will do, we'll go ahead and walk through it. Get our main function down here. That, you know, all it does is take in some command line arguments and then pass those command line arguments to read JPEG here. And then read JPEG, all it's going to do is take those stripped command line arguments in as our in file and our out file. Obviously, we're going to have to add some more stuff here as far as like, you know, need to add desired output size, etc. So it's definitely something we'll have to consider as we get further into this. And I also just want to say I hadn't really made any content for like a month. So yeah, I was lacking on that front, and I went backpacking this past weekend, and I was like laying in the tent, and I was like, man, I need to like make YouTube videos. Because it's pretty fun, and sometimes I end up learning more by just talking about this dumbass shit than if I was just sitting here in my head about it. So, all right. Oh yeah, I got a new MacBook. If you can't tell, I've had a MacBook for a while, but it was a dual core i5 Intel based, shitty battery life. Could I have done streams on it? Yes, but it was getting near its end of life with Mac OS, but also it had an issue with it started suffering from FlexGate, which is a stupid ass problem that MacBooks get from the 2016 to 2017 model years, that the display cable that hooks the monitor up to the motherboard or whatever the hell they call it in MacBooks, the damn whatever something board, some fancy name, logic board, I don't know, some dumbass shit. But yeah, that little ribbon cable that runs from the display port or the display to there goes bad. I guess it's soldered onto shit and back because you have to buy a new display apparently, and that was $500. So I was like, fuck it, I'll get a new MacBook. So now I might be able to do some Xcode stuff. comfortably. Like I said, I could scoot by on my old MacBook, but also had a 128 gig SSD that was taking up like 40 gigs of it by the damn operating system itself. So working with a lot more storage now. Let's go ahead and walk through the code. I kind of need a refresher, even though I spent last night kind of just staring at it. It's not really too complex at all for someone who's yet to really build something of their own in C. I've had a lot of time writing C, the actual, as far as the actual syntax is concerned, but when it comes to the actual nitty-gritties of building a project, that's what I'm trying to accomplish with this. This is going to be my first real C project that I'm committing to really get a grasp on the language and how everything works together. So yeah, we have this read JPEG function. That's where I left off earlier. And all it's going to do is it's going to define and initialize our struct, our decompression struct, which all that's doing is it's holding all the metadata that relates to our image that needs to be decompressed. So when we pass in a JPEG image into C, we're going to have to decompress it in order to actually read the actual data we want about it. So really, there's a high-level overview that I've kind of noted here. We're going to initialize a few structs that are required for our program to work. And then, yeah, we're going to do just an OG open file. We're going to read as binary. Got some error checking in case, you know, it's a trash file or something like that. And then we store the file pointer as this in file pointer, of which then we provide to our decompression struct. So our decompression struct is going to know where our error handling struct lives, or how to communicate with it, which is this. And also providing the in file pointer, so our decompression struct actually has access to the actual file and memory. We're going to read the header data. We're just doing some debug printing here. And then we actually start this decompression process with this line. If you can't tell by the aptly named JPEG start decompress. Now this is where it starts getting a little hairy for me. Now we are calculating a row stride. Well, what is our row stride and why is it important? Our row stride is basically just what is the length of a row in our image? Yeah, I think row is this way. So, you know, if you have a screen, it's 1920 by 1080, or you have an image that's 1920 by 1080, for example, like a desktop background. The rows are the long ways, right? You know, the way a 1920 by 1080 image is shaped, you know, you can infer that, you know, length times width. So we're just, via reading the header data, we are then able to access things like the output width and output components. Now this is, the output components is where it kind of, I had this like, oh, okay, that makes sense moment after I started playing around with some of the raw pixel data. And basically, the way we are able to calculate a long enough row stride in order to store all the data about the pixels in a single row, because you would think, you know, this here, this 3360, that would be our row stride. That's how long the row is. Well, the thing is you can't represent every pixel on a row with just 3,360 segments of an array. So RGB values are pixels, right? And that's 3 values. That's what the output components comes from. So we have our output width times our output component. So in order to represent 1 pixel, we're going to need 3 numbers, if that makes sense. So, 1 red, 1 green, 1 blue. So our row stride isn't just 3,360. It is 303,060 times 3, which there's 3,360 pixels. But in order to represent the color data for all those, we're going to need, So that leads us to 10,080. Next, well, actually, I'm going to go up here to this and just kind of talk about this here. This demonic thing is going to be an array of all the pointers to our rows. So this is kind of what I spent time last night trying to wrap my head around, exactly why we do it this way and exactly how it works. So this is a lot of pointer magic bullshit that's going on. So in order to write to all of our rows of our image, so we don't have to worry about columns. We just want to write it row by row. We're just going to iterate for the amount of columns, if that makes sense. So like if we have 3,000, or if we have an image that's 3,360 by 2,100, we know that we have 2,100 rows that all need to be 10,080 elements long in order to represent every pixel of our image. And the way this is written, that's just not a hard-coded value, but that's when I'm talking about 3,360 and times 2,100, it's just in reference to the image I've been using to test the program. So what row pointers is an array of a bunch of 2,100 pointers that point to each row in memory of all the rows that we need to allocate, right? So we're doing a memory allocate, or a malloc, of the output height, which is 2,100. So 2,100 rows. And then the size of unsigned char star, which let's I guess that's one. I didn't really look into this too much. Unsigned char star size, 1 byte. Yeah, I know a char is 1 byte, but is a pointer to an unsigned char. So okay, makes sense. Yeah, so it's literally just saying times 1 times size of. Whoa. All right. Obviously, I've copied some code from certain places. I don't understand this C pointer magic, but I'm done looking at this and that and C. Screw that shit. We're just gonna get knee deep in the weeds and mess around with this bullshit until we understand it. And if we don't understand it, we're just gonna butt our heads up against the wall until we do. So I don't even think this. I might have dropped this. Ignore my quick CLI tool for cache. I was having a conversation here. But yeah, I was trying to make sure with Grok that my thing was working the way it should, because I don't know what the hell this is supposed to look like, right? but I've got a decent grasp now. Sorry, I'm getting derailed here. So this is basically saying, hey, allocate memory for 2100 rows times size of... What the hell does... You know, what does size of look like? Size of unsigned char star. What does this look like? Paste. Okay. Okay. Can I please copy and paste this? What does that look like? %ZU. Okay. Hey, I was close. I had the U. Cool. Now we can see what this value equates to. I usually write on my MacBook, so it's a little different. On my MacBook keyboard, I'm using my 5-year-old Keychron K6. What the hell am I doing? Make bin image test images JPEG. Okay, full buffer size. So okay, that's equating to a size of unsigned char star. Make so 8. So 8 bits. Okay, so on a 64 byte system, it would be 8 bytes. So, okay. On a 32-bit, on a 64. Is it? Oh, okay. I need to keep fucking reading sometimes. Is a pointer to an unsigned char, and its size depends on the architecture of the system it's running on. Blah 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 blah. Yeah. So, yeah, I was about to say, I was like, okay, it understands, or I understand that a single character can be represented by 1 byte, but how the fuck can a fucking long ass memory address be represented by 1 byte? It can't, because that is impossible. It's 8 bytes. So okay. Yeah, that's 8 bytes. So 2100 times 8. So why the hell are we doing that times 8? What does that achieve us? Row pointers. So 2100 times 8. Let's honestly just get rid of this. Like, did I write? Okay. Is this still gonna give us what we want? Yeah, why are we multiplying that by 8? An array of row pointers. Um, it's starting to make sense. I'm thinking about it. So we need 2100 rows, but we also need to be able to store all of our pointers. We got to do some research on malloc. Malloc in C. Can I just get like... Excuse me. I want to make sure that my stream is like going and shit. Cool. Does it show anything I should... Cool. Whatever. It works. Okay. Got distracted. So... Okay. Allocate size bytes of uninitialized storage. Yes. So. Okay. So malloc isn't doing some weird shit. Where it's like allocating these arrays and oh gosh, my brain is falling apart. You know, it's been a good day today. Worked on the Java app at my work. Getting it ready to ship out. Washed my car. That was cool. So getting to this, just frying my brain a little bit. So setting. Okay, let's just take a deep breath. So we have this row pointers that we want this. We want that there because that's telling the total amount of bytes that we need to allocate is 2100 times 8 because we need 2100 rows that are able to, and these rows will be 8 bytes. Yeah. Because we need 8 bytes to store a pointer memory address. Yeah. Okay, that makes sense. Yeah. We can get rid of this. So we've covered, we've covered this read JPEG. We've covered the main function, read JPEG, very simple. defines, initializes the struct, and passes it to our real medium do read JPEG. This up here just opens a file. We read our header data. We get the stuff we need. So, yeah. Coming back to row pointers, sometimes I gotta realign myself a little bit. The reason we have this is so we have this long list of addresses. So when it comes to allocate this huge ass buffer of ours with all this pixel data, we know where to allocate the data to. We have an address for every row, essentially. So yeah, right now I'm thinking too much into this. This shit's not really doing anything. It's just a big fucking chunk of memory that's been allocated. We haven't done anything with it yet. It's just memory allocation. We provide the open file to our decompression struct. We read header data, print some header data, start decompression process. Row stride is already kind of went over that. That's the length of our row. And then we have this full buffer that is defined initially up here. We set it to null. You know, actually, we're doing it up here. This is sort of just messy code. Why did I make this exception for to where I was gonna initially define it and then memory allocate? Nah, we'll just memory allocate it up here to clean up our code a little bit more. And then keep actually pressing in. Yeah, let's just yeah, allocating big ass buffer to store whole image RGB data. Yep. Cool. That's what we want. Yeah. Got our full buffer up here. Let's make sure this still works for some reason. If it just decides to shit out. Segmentation fault. Oh, brilliant. Brilliant. Okay. That's not good. Maybe we do want to. So wait, why in the hell do we got to do that? Do we got to do that? I guess, you know, I could just put it here. This is gonna work, right? Segmentation fault. Oh. So wait. Is this segmentation fault the result of trying to use these values before we read the header? But how the fuck is line 35 working? I don't know. Make segmentation. Okay, now we're not gonna fuck with that. We had it working. It's gonna work. Yeah. Back in business. Okay. Yeah, calculating row size. Been over that 1,000 times. Allocating our full buffer, which is just our width times our height times our output components. Width times height times output components. That's going to... How many elements do we need to store the RGB values of every single pixel in our image? Which, in our case, it's somewhere around 21,168,000 pixels. Numbers. So, and then we're having this for loop here that actually allocates our row pointers. So this shit was actually making my mind explode last night. I was like looking at it, right? And I'm like, okay, but how in the bullshit are we doing math like this? Grok broke it down. Grok broke that shit down for sure. Was like, oh man, that's pointer arithmetic. It's just calculating how many bytes or something like that. Basically saying full buffer you know what? I already forgot what the fuck this shit was doing. Okay. Yeah. So what this is doing is it's jumping ahead. On each iteration, it's basically making sure our rows are a certain space apart in memory. Jumping forward the length of our row amount in bytes. So yeah, because you have to think in our buffer, the way we'll be able to determine which row we're on is via some sort of arithmetic that you know, our first row is 0 to 10,080. Our second row is blah, 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 up to 22 something or 21,000 something. 20,160 or something. So 21 or 20,160 will be the red value of our second row of pixels. So we kind of demonstrate that here about to see our first pixels data would be 0, 1, 2. And it's red, green, and blue values. So this is just doing some allocation stuff. And then this is showing, you know, the actual address for each row. We'll recomment that out. And then this is where the stuff actually happens. This is where we're writing into our buffer. This is how we're getting all of our pixel data into our buffer. So then we can actually start working on our program. Which its entire point is to resize images, right? There are libraries out there that were recommended to me through Google searching on, hey, you know, building a command line tool to do some image resizing is cool. You know, you can do it with libjpeg, which is what I'm doing, and basically hate yourself, or you can do it with some easier library. But I don't know. I think for close to a year or so, this sort of side of programming has just really interested me. I like playing around with the memory and it being so sensitive, and I don't know, it just feels like I'm writing something that's very optimized, and there's not a lot of fluff. you know, I mean, this entire program, once it becomes fully together, is literally peeling apart a JPEG, decompressing it, writing all the pixel data, 21 million bytes or whatever, in my case, of this test image I've been providing it, to this buffer. So we have all these numbers in this buffer. We have access to every pixel. And then we'll implement something like the nearest neighbor algorithm to actually run through this entire image and operate across these 21 million pixels. Really excited to see how fast that happens. Because the entire point of this program is like, you know, it's probably something that exists a million times over out there. I just wanted to do it. But this is a simple tool. You're working with fucking React or whatever sort of front-end slop framework. You know, you got an image in there. Instead of offloading that resizing to CSS to your actual application, you know, you don't have to like open up Photo Viewer or Microsoft Paint or GIMP or some shit just to resize an image, and we can just be like, hey, this imagey, my image, make it this size, you know, whatever. Obviously, you know, there's a lot of worries of like, okay, well, how the hell am I supposed to know the appropriate aspect ratio, the appropriate size to match the same aspect ratio, but to get close enough. But we'll cross that bridge when we get there. I just want to be able to resize an image with my own implementation of this nearest neighbor algorithm, which is really the next step. I've just been spending the last few sessions in front of this code just trying to understand it better. Making comments, deleting comments, writing notes, blah, blah, blah. Eventually I will feel comfortable enough to just start hammering this out, but then I'm like, okay, how the hell do I implement this, right? I kind of get the gist of it. We're going to have to do some research, perhaps on stream, of how to implement nearest neighbor across my pixel data. So it's a lot, in my opinion, but it's pretty cool, I think. So look, let's just do a little example here. Like I explained, we know our row stride 10,080. I know you can't see where I'm pointing, but up here. So we can take this pixel 0. I don't know. Let's see. We can do some quick math. At the end, this will be 3,000. Pixel. I don't even. So. There's 3,000 pixels in a row, 3,360 pixels in a row. In order to represent those pixels, we need 10,080 elements. Sorry if that just sounds like I'm yapping in circles, but yeah. So 3,360 would be the last pixel in our row. But let's try that. 3,360. So this. We're going to print the first pixel of our first row and the last pixel of our first row. So let's, this would be, so 10,080 would be the last element of it. So 10,078, yeah. 10,079, 10,080, yeah. Now let's see if this will compile. How that looks. Make. Okay, cool. Yeah, it worked. That should be right. Well, yeah, that's what makes sense to me. first pixel of first row yeah. Okay. So I don't even think I really elaborated on this while loop, right? This is where we're writing into the buffer, right? We really don't have to. We can kind of set this as a void here, and it will work the same way. I was just storing that value as an integer to just see the iterations, but I'm actually going to keep that. So, yeah. Ignore the int rows red. That's just debugging thing. We might have a use for it later on. But we're using this JPEG read scan lines. We're pointing to our decompression struct. And we're pointing to our row pointers. So let's look up what the technical arguments of this are, actually. JPEG read scan lines. JSamp array scan lines. So this is our C info decompress pointer. Yep. Max scan lines. Max lines 1. Return up to the maximum number of scan lines of decompressed image data. This should be less than the number requested in cases such as bottom of image data source suspension operating modes that emit multiple scan lines at a time. Image data shall be returned in top to bottom scan line order. Yeah, so we're actually providing to it where to read the scan line data into, which is our row pointer's address. So it's tracking this output scan line. We can actually see this here if we let my thing do its thing here. And then decomp output scan line. Yeah, we can actually see it iterating through our 2100 rows. So that's what output scan line is doing, is it's keeping track of that. So it's saying, you know, read into the first address of row pointers, read into the second address, read into the third blah blah blah, all the way up to our height of our image, which is, you know, our condition here. As this increments, once it stops at the height of our image, we'll stop. And the 1, that's because we're number 1, baby. Yeah, so all I'm concerned with is that it's doing its job, you know. I know that's antithetical to me running around in circles in my head for the past 20 minutes, 30, I don't even know how long I've been streaming now. 45 minutes. Holy shit. And I've not written a single line of code. I honestly just wanted to kind of talk. I don't know how much, I don't know if I'm even going to start on this resize JPEG function today, but hey, we've got a start. We've got a resize JPEG function that accepts a pointer to our buffer, our huge buffer full of all our pixel data. So we're able to access that in memory and actually play around with that pixel data. And then just for now, instead of worrying about stripping the command line arguments and getting a desired output size, we just got output width, output height, and I capitalize these just to kind of denote that, hey, this is not going to be the final um, thingy here. So yeah, no return here. It's just gonna do its thing. It's gonna look through all these pixels, resize it with this algorithm, and then it's gonna write a file somewhere else, which we'll probably need a write file function up here as well. Not sure exactly how that's gonna look yet. So yeah, let's one more time from the top. We got this read JPEG function inside of our main function that kicks our program off. We've got our main function. It's C. This is sort of the main function of our program. It's going to really kick off this whole chain of events that everything else is going to follow. So here we're just decompressing or initializing our decompression struct, which is really the entry point of all JPEG reading. This little guy is this little helper function. I could probably move this over to my helpers.c up here. Haven't done any code in here yet. But yeah, then we've got this big ass do read JPEG. I could probably strip shit down into separate functions, but this is doing its thing right now. We start off, we've got error handling, we're reading data, we're allocating buffers, blah blah blah, and then we're able to actually see some pixel data. So it's contained well enough at this point. So yeah, from the top. After we basically finished this function. We've got our data. We've got our pixel data. We just need to now start doing some crazy shit here to then play with the data. Before this, I never messed around with buffers. My pointer knowledge was very, very sparse. I had a couple aha moments with pointers in the past that I was like, oh, I'm running this function that does this simple thing, and I don't have to pass the whole, like in Python, you just pass a variable in. In C, you're going to pass a reference to that variable because that variable already exists somewhere in memory. There's no reason to package it up and make a copy of it just for another function to use it for the meantime, etc. So we're actually going to be editing that while it still persists in memory. I guess that's how it works. My understanding. Yeah. So that's the next step. We're going to do that. I've spent 50 minutes just yapping about my code. And if you are interested in building something with this as well, I use Grok. Grok to instructing an AI agent to be your mentor and explicitly telling it, hey, don't give me code. Damn, and the album just ended. Imagine that. That's how you know it's time to wrap this shit up. Yeah. But libjpeg, this shit's like over 30 years old probably. So finding shit about it, it came out in 1992 originally. So this resource here on GitHub, this example.c, along with using Grok as your mentor, will get you very far. And it's really helped me just boot up and get something going. So yeah, I guess today it wasn't really any programming. I just kind of wanted to share what I've been working on. So yeah, that's that. I'm gonna hop off the stream, go relax for the day. Like I said, I worked today, and then just hopped straight on here and started streaming and just started yapping. So yeah, as always, let me know if you want to see more content like this. I will return to my practical C programming walkthrough example, blah blah blah. As I said in that last video, may do it in a format like this because it's really no different from how I was doing my recordings, because I just kind of hit go and then I sit here and talk and try to solve problems. So yeah, that's what I've been working on. We'll return to it. Expect another stream maybe this week, maybe next week. We'll see. I don't really want to make progress on this without streaming, but if I do, then it'll be okay, you know. I think what really has leveled up my programming skills over the last few years is I try to make it this like disciplinary action of code X amount of hours on X days during the week, and then do this after work, and then blah blah blah. You need to study this amount of time, and it's like just write code, man. If you get a hunkering, you're laying down in bed, it's 11:30 at night, you got work in the morning, just whip out the laptop and just look at code. At least look at code, print some shit, just mess around with it, you know. That's really what all this is. I don't know. The more you do it, the more you'll fall in love with it too. But yeah, what am I saying? I don't know shit. Don't listen to me. Thanks for watching. Expect more streams. Y'all be safe, and happy C sessions. Oh yeah, y'all want to check this really cool eBay shirt I got off eBay. I don't know if you guys have ever heard of Turbo C, but it's an old C IDE, and I just love C, man. I love C. It's cool as shit. I got this dope vintage shirt. It's an old ringer on this Hanes tag. It's a Turbo C shirt. Pretty sick. But yeah, I'm just yapping. Y'all, oh, I just doxed myself. Yeah. I live at 1446 Clayton Court, Bowling Green, Kentucky. Pull up on me. Y'all be safe.